Hey, welcome back, you crazy cats. Today we're going to learn about acceleration, the fact that it's a vector quantity. Acceleration is the slope of velocity time graph. Displacement is the area under the curve of a velocity time graph. And constant acceleration allows for kinematics to work. And we'll be dealing with the standard of constant acceleration. Alright, so today we're going to start working with these kinematics. Some things that I want you guys to get used to doing is to make a list. Alright, so the first thing you need to do is to get used to making a list. So with this then, it says you're designing a time travel machine for small cars. One kind of car that might use this machine must reach a speed of 35.8 meters per second to make the jump, and it can accelerate at 1.5 meters per second squared. It says if a drag strip is 200 meters long, can this car reach 35.8 meters per second to make the jump? What is the minimum length it must be? Well, we're not going to actually solve this. We'll do this in class. But what we're going to use this for right now is to actually make that list. So as I look at this, you are designing a time travel machine for small cars. One kind of car must reach a speed of 35.8. So that would be VF. And my pen is not allowing me to write on black. Alright, so we've got something that's kind of working here. Still not real happy with it. But VF equals 35.8 meters per second. One of the things they don't tell us is the initial velocity. And when they don't give you initial velocity, typically we're going to assume that just means it's starting from a standstill. So we're going to say 0 meters per second here. They tell us the drag strip is 200 meters long. So XF, and we'll get into this quite a bit today, is 200 meters. Again, they don't tell us the starting spot, so we're going to be able to assume that XI is the 0 meter mark. They also tell us that it can accelerate at 1.5 meters per second squared. And if you'll get used to making that little list right there, this is going to be a whole lot easier for you guys today. But there's our first example of making a list. Alright, well, let's get back to some other stuff before we get back to doing some math. Acceleration is a rate at which velocity changes. So on here they give us an equation for acceleration. Average acceleration is the change in velocity over the time to make the change. So up here they have this triangle, which means delta, or change in velocity, over the delta, or this triangle, or change in time. And they give us this equation down here of V2 minus V1, or V minus V naught, or sometimes you'll see, let's see if this is going to write for me. I bet it does not, but you'll see VF minus VI, alright, over TF minus TI, meaning final and initial. Acceleration means that the speed of an object is changing, or its direction is, or both. So acceleration means that we have a change in speed or a change in direction. So for example, down here, acceleration could be that the speed changes. Here they have 20 kilometers per hour, here they have 30 kilometers per hour. Or it can go from 40 kilometers per hour to 0. So we could have a decrease in magnitude of the speed. Down here, alright, change in velocity direction, but not the magnitude. So here it was going 80 kilometers per hour. Here it's going 80 kilometers per hour, but notice it's no longer going up. It's kind of going up and to the left. Or the same thing here. We could have both magnitude and direction. So here we have this car that was going 60 kilometers per hour, but it changes direction and it slows down and it's now going 40 kilometers per hour. So acceleration could be a change in speed, or it could be a change in direction. It could be either of those two, or both. Alright, acceleration may result in an object either speeding up or slowing down, or simply changing its direction. And we kind of go into a lot of detail here. So this takes us into our first kinematic equation here. If the acceleration is constant, we can find the velocity as a function of time. So we have velocity equals v naught plus at. You're going to see me refer to this quite often is vf equals vi plus at. It's final and its initials, what that f and I stand for. They're not really a part of the equation, they're just subscripts which help us to designate the difference between one velocity and a different velocity, meaning the object's final velocity and the object's initial velocity. Different books, they'll use different ones, and this one's going to use v and v naught. V naught meaning the initial or the original. In this case, when we have a velocity and a time graph, down here they have the time, velocity and time, they're also throwing at us right here right away that the slope, all right, so we have velocity over time, would be the acceleration. Right? So here we'd have positive acceleration, constant acceleration, because the slope is constant. Here we'd have negative acceleration because the slope is going down. We still have negative acceleration here when it's below the x-axis, and we still have negative acceleration even when it starts above the x-axis and goes below the x-axis. It just simply means that it was going with a positive velocity, and now it has a negative velocity. So this slope tells us the acceleration. It does not tell us the direction that it's going. We'll talk more about this here. Alright, other kinematic equations. We have x equals x naught plus v naught t plus 1/2 at squared. So what this tells us here is that this would tell us the final distance an object's, how far an object's gone. We have its initial position. We have its initial velocity and how long it was going that initial velocity, plus some type of acceleration, 1/2 at squared. We also have v squared equals v naught squared, or the velocity that it finished at squared equals the original velocity, or its initial velocity squared, plus 2a times the change in displacement, or this change in position, or displacement. This right here, remember, is our displacement equation. So x minus x naught, or the final position minus its initial position. So constants there. These are all the equations we have derived for constant acceleration. The correct equation for a problem should be selected considering the information given and the desired result. If you make a list, it becomes a whole lot easier to decide which equation you're going to use. Alright, so here's our first problem. I'm going to go through here and make a list. It's very similar to the one we had at the beginning of class where I made a list, but now we've got some different numbers. You're designing an airport for small planes. One kind of airplane that might use this airfield must reach a speed of 27.8 meters per second. So VF equals 27.8 meters per second, and it can accelerate at 2 meters per second squared. If the runway is 150 meters long, so XF is 150 meters, can this airplane reach 27.8 meters per second for takeoff? If not, what is the minimum length it must be? XI is 0. They don't give it to us, so we can assume it to be 0. And we can also say it's taking off, so we know that planes start from a stop, so the initial velocity here would be 0 meters per second. So, now, if the runway is 150 meters long, can this plane reach 27.8 meters per second for takeoff? So what we really, this question is a little bit tricky. What they're trying to get us to find here then is what is VF after 150 meters given this acceleration, this initial velocity, and this distance. I'm going to solve for VF. That's just the math. The physics then is if I get an answer of 150, or sorry, if I get an answer of 27 meters per second, and it needs to be going 27.8, would it be able to take off? Well, no, it's not going fast enough. If I get an answer of 28 meters per second or faster, would it be able to take off? Yes, because it only needs to be going 27.8 meters per second. So I need an equation then that uses VI, A, XF, and XI. So as I look at these equations right now, all right, I know this is my XI, that's my XF, this is my VI. I have equation 3. Notice equation 1 doesn't have any x's, so I'm going to get rid of that one. Not really erase it, but I'm just not going to use it. Equation 2, you guys aren't going to use it very often at all. We'll talk about that in the future. Equation 3 is our displacement equation. Right now, I have an initial velocity, initial x, and a final velocity. But the problem with this equation here is we don't have any time. All right. In our problem, it never gave us a time, so I can't solve for two variables. I can't solve. This one doesn't even have final velocity now I think about it, so that one's not good. This one down here has a final velocity. It has my XF and XI. So the only variable I have missing in this equation is VF, so I'm going to use that one. VF squared equals VI squared plus 2XF minus XI. In this problem here then, VI is 0. So what we typically do, if something's 0, we just cross it out because I don't need it in my problem. XI is, oh, there's an A in there too, I forgot. There we go. XI is 0, so I'm going to cross it out. And I'm left with VF squared equals 2A times XF, because 0 plus anything is just 0, and XF minus 0 is just XF. So now I've simplified this equation quite a bit. So I'm going to plug in what I know. 2 times 2, because my acceleration over here is 2. XF is 150. So I get 2 times 2 is 4. 4 times 150 is 600. VF squared equals 600. So now I need to simply find what the square root of 600 is. And VF turns out to be 24.5 meters per second. So now comes the physics. Is that fast enough to take off? The answer is no. Alright, on here. Let's look at this graph. What is the average speed of this object? Well, now we're going to do some work here with graphs. This graph is different than what we had yesterday. We now have a speed and time graph. Yesterday we had a distance and time graph. So the average speed can be found by using the slope. Right? So I've got to find the slope of this graph. I'm going to pick two ordered pairs. I'm going to pick one here. I'm going to pick one here. This is 3.54. And this one here is 8.8. So to find the, oh shoot, I'm sorry, backtrack here. I wrote this wrong. This here should be the average acceleration. I know what I wanted, I just didn't type it in there. And then right here should be acceleration as well. Alright, so let's go back to this here again. This is my x1, y1, x2, y2. I'm simply going to find the slope the same way you would have in Algebra 1. 8 minus 4 over 8 minus 3.5. And we're going to get 4 over 4.5. Which gives me approximately 0.89 meters per second squared. There we go, second squared. Again, because it's speed over time, so that's my acceleration, 0.89 meters per second. I'm using the black one because it is my best fit line, which is going to give me the average. Question 2 says, what is the instantaneous acceleration of the object between 6 and 7 seconds? So to do this one, I'm going to use the orange because this right here is the actual graph. It wasn't the best fit line. This order period here is 6, 6, and this is 7, 8. Again, this is x1, y1, x2, y2. I'm going to use 8 minus 6, 7 minus 6, and we get 2 over 1, or 2 meters per second squared. Now the next question says, what is the displacement of this object? Well, that kind of takes us into the next thing. Students are usually really good at finding the acceleration and speeds because they know how to find the slope. But there's another thing we can do with the graph, is we can multiply. To find the slope, we divide it. I'm going to tell you to find the area is to multiply. And what we do then with that is we need to find the area of a certain figure. In this case, we want to go between 4 and 5 seconds. So I want to find the area of that right there. Well, this base is 1 because 4 to 5 is a distance of 1, and then it goes up to 5 and it's flat, so it's 5 tall. So 1 times 5 equals 5, and my displacement would be 5 meters. Now let's talk about why it's 5 meters. Basically, we're multiplying. So forget about all the numbers and let's just do some dimensionality. Let's multiply our units. Over here on the left I have meters per second. Over here I have seconds, so when I multiply them, I get meters per second times seconds over 1 if I change it to a fraction. The seconds cancel out and I'm left with just meters. So what I want you to understand is that the area, when you find the area on an acceleration graph or a speed versus time graph, you're going to get an answer that gives you units of meters, which would be the displacement. So what that tells us then is that whatever object this was, between 4 and 5 seconds, it moved a distance of 5 meters. Its displacement was 5 meters from where it was. Well, hey, that's everything I have for you guys today. Here's what I want you guys to do, all right? Why is an acceleration a vector or scalar quantity? Acceleration is found where on a velocity time graph? Displacement is found how when looking at a velocity time graph. So I've given you a graph to kind of look at. Do your best with it. I'll catch you on the flip side.